Okay, so let's start. So last Monday we discussed about the point and interval estimate, and also we thought of the mean value or the sample mean, and then used it as an estimator for the true mean value mu, and then we considered several different cases where we know the true variance value, and also the other case where we have no information about the true variance. In that case, we replace the true variance by the sample mean, and also in this case we use a t distribution instead of just a standard normal Gaussian standard normal random variable. And then we considered like one sample. This kind of one sample case and then the two sample case. So again, the sample is the subset that you obtained from the total populations, and then when considering the two samples, which means you obtain two sets of samples from two different populations, and then depending on their variances are known or unknown, but they are still assumed to be the same, we consider this interval estimate for the difference between the means of these two populations, which is just mu1 minus mu2. Okay, and then at the last part of the class, we consider the most difficult one, where these variances are unknown and also they are different. So in these cases, the difference of the sample means, which is x1 bar minus x2 bar, that is still following the t distribution, but in that case, the degree of freedom of this t distribution had this complicated form, which we didn't cover. Okay, and then today we will start with this paired observations. So in the case of paired observation, the setting changes in the following way. So we start with the two population and then obtain two samples from each of these. One sample from each of these populations. So we have maybe those people living in Seoul and Daejeon, and then we obtain the sample from each of these populations. And then we first compute the mean of each samples. So we first compute like a mean height or average height of 10 samples that we obtained from Seoul, and then also we compute the mean of samples or those people that we obtained from the Daejeon's population, and then we considered their differences. But in this case of paired observations, let's see. So again, we have two population A and B, and then obtain their own sample that may have like 5 different samples, and then we compute the mean value or the sample mean, right? And then we consider their differences in this manner. But in the case of paired observation, we actually obtain a pair of sample from each of these populations. And so let's represent it as a circle, and then see. Representing it as a triangle for the samples obtained from B, and then we consider this pair as one instance of our samples. So, let's see. When we obtain 5 samples from each population, they are actually paired. Okay, and then we compute the differences from each instance from our sample, and then we compute their mean value. Okay? So in this overall process, 2 steps have been changed. So we first compute the sample mean from each of these samples, and then compute this, the difference of sample mean. But in this case, we obtain a pair of instances from each population A and B, and then assuming we obtained 5 pairs of samples, and then we compute the differences from each sample, and then we consider this as a new random variable that we want to estimate. Okay, so in this specific case, one example corresponding to this paired observation is as follows. So, so you want to obtain the sample for a person's height, and then suppose our 2 population is just a man's height and a woman's height, and then you just obtain the samples independent separately, and then consider the difference between these 2 sample means, and then these are what we handled until last time. But in this case, our samples are assumed to have some relations. So we assume some relations between these 2 populations. So when obtaining a man's height and woman's height, suppose these 2 people are the children of the same parents. Okay, so from one parent, we obtain a pair of like male or female or just boys and girls as a pair, and then consider their differences or compute the differences from each pair of instances. Okay, so from one parent, the man's height was 185, and then the woman's height, who is the sibling, her height is 169. And then another, the boy is having 170 centimeter tall, and then his sibling, who is a girl, is maybe 155 centimeter tall. Okay, so in this case, what we would have done previously is we just take or we collect those samples separately, and then compute the sample mean for those men, and then compute the sample mean for women, right, or girls, and then compute the difference between these 2. But in this case, we just first compute the difference. So in this case, it's 16 centimeter, and in this case, 15 centimeter. Okay, and then we consider the differences or the probability density functions for those random variables. So these are called paired observation. Okay, so in this case, if we do not know the variance, the true variance, and then this random variable, so this random variable d bar, which is just a difference between a pair of observations, which is like 16 and 15. So those variables are still following the t distribution, just like the separate sample cases. Okay, but in this case, the only part that changes is how we compute this sample variance. So previously, when computing the sample variances, we computed the variance for x1 and x2, and then we just simply sum them up, right? And the reason why we do just simply the summation on these two is because those two sets of samples were independent, since they are statistically independent. And so, usually when considering the variance, which is maybe the difference of the two random variables, is computed based on this formulation. So we compute, or we just add the two parts of the variance from each random variable, and then we also consider their covariance part. Okay, how they increase or decrease together. Okay, so that was the definition of this covariance. So if one variable is increasing, and then in that case, if the other variable is decreasing, then we consider this case as a negative covariance or correlation coefficients, right? But if they have a positive correlation, if one variable is increasing and the other, it means the other variable is also increasing. Okay, so in this specific case, I mean, if we assume this a positive correlation, so in this specific case that I gave you, so in this case we considered the height of the siblings who were born from the same parents. So their heights are somehow positively correlated, right? So if we see one boy is really tall, and then his sibling will be also likely very tall, right? So it means their heights are positively correlated, right? So in this case, so it means when considering this paired differences, I mean the difference from this paired observation, we can no longer assume that these two samples are independent, right? So they are clearly dependent. And then, if they are dependent, this covariance or correlation coefficient part will be non-zero. And then, in this specific case, where we can expect some positive correlation, and then it means this part is some positive value. And then, since we are considering the differences, right? So our new random variable is formed as the difference between the two random variables, right? So when considering the covariances, I mean the variance of this new random variable, the variance of each random variable is contributing to this covariance in this variance of the new variable. But at the same time, we see this part that are contributing as a negative sign because of this negative sign, right? So, if they are positively correlated, then the overall variance for this new random variable x1 minus x bar, x1 minus x2, that should have smaller variance compared to just a simple summation of these two. Okay. So this sample variance will be smaller than just simple summation of the two sample variance. Okay. So in this example, back to this example. So those values from this paired observation setting, those values will have smaller variance compared to the case where we considered this separate observations and computed their sample means first, I mean independently, and then consider their difference between the sample means. Okay, so in this case, the variance will be higher than this case because those two values are positively correlated. Okay, so in other words, on average, I mean suppose the average height of a man will be 170, maybe 175, and then the average height of a woman will be like 158, and then the difference will be like 17 centimeter, and this value will be smaller in this case. Okay. No, I mean, so let me correct, let me say it in a more exact way. So this is just a mean, so this difference will be the same. I mean, the mean value will be still the same as 170 centimeter, but how different each of these differences from this average value of sample mean, they will vary much more in these cases compared to these cases. So this case will be having a lower variance or smaller variance, which means it will have a kind of narrower probability density function. Okay, so that is the notion of this paired observations. And then the actual interval estimate is simple. So we just use this t distribution, and then the sample variance divided by the square root n. Okay, which we would just like we would do in the other non-paired cases. Okay, so that is the notion of this paired observations. And then we now move to the case of this proportion estimation. So the proportion estimation, in this case we consider the Bernoulli case, or it's a multiple experiments version, which is binomial distributions. Okay, so here the main purpose is that we want to estimate the true probability of some event happening or not. So clearly there are two event outcomes, whether the event happened or not. Okay, so in terms of the random variable, it will be either 1 or 0. Okay, and then from some experiments, or by obtaining some samples from these experiments, we want to estimate the true probability value. So suppose we have a coin, and then we are interested in estimating the probability of seeing the head of this coin. So it's like front, and tail means back. Okay, so it's like front side or back side of the coin. But if we consider just a usual coin, and then this probability will be exactly 1/2. But this coin is some special coin, so we don't know yet the true probability of each event. Okay, so these two events will clearly have the probability that have the summation of exactly 1, of course. So suppose we are interested in this event of seeing the head or front side, and then we want to estimate this probability p. And then in order to estimate this probability, what we would do is just repeat the experiments of just flipping a coin. Okay, we just throw the coin many times, and then suppose we have 1,000 times of a coin flipping or coin throwing, and then exactly 600 times of head or front side were observed. So in this case, we can simply estimate the true probability of seeing the head as 600 over 1000, which means 0.6, right? Okay, so let's think about this case from the perspective of binomial random variable. So this repetitive trial is exactly the one kind of instance or one trial of binomial random variable where we have the parameter n as 1000 and then p is still unknown. Okay? But in this case of binomial case, the random variable x in this case is the total number of this front side occurring, right? So in that case, the random variable x is equal to 600. And then this binomial random variable or binomial probability distribution was telling us the exact probability of observing 600 times as the value of an x, okay? But in this case, this n and p, which are the two parameters of binomial random variable, should be already known. So when they are known, and then we can compute the probability for x or the number of front side being equal to 600, right? But here the problem is, or the problem setting is that we do not know the true value for p. Okay? So in this case, we consider the mean and the variance of this binomial random variable. So the situation is we fix the total number of trials. Yeah, so that suppose that value was 1000. Then we still do not know p, and then in this case of random variable x, which represents the number of events of seeing front side of the coin, the expectation value is represented as np. Okay, and then yeah, so the variance of x bar, variance of this x for this binomial random variable is npq. So that's what we studied previously. Okay, so in this binomial case, if we divide this random variable x by n, so again, x is the binomial random variable, and then if we divide it by the total number of trials, okay, in this case, the expectation value for this new random variable will be exactly the true probability p that we want to estimate. Okay, so in this case, we are considering the exact process that we did here. So we tried, or we did 1000 trials, and then we observed 600 number of front face, and then we just simply divide by these two numbers in order to estimate the true probability p. Okay, so from the perspective of a binomial random variable, this one will become n, which is a parameter for binomial random variable, and then this 600 is just a random variable value for binomial random variable, because binomial random variable, the random variable has the meaning of the total the number of events occurring. So x divided by n, which is our new random variable, will have the expectation value for this unknown parameter p. So that way, x over n, okay, this value can be used as an estimator for the true probability p. Okay? So if we compare this case with the previous case of a normal random variable where we want to estimate the true probability, the true mean value mu. In that case, the random variable is just one time of sampling the normal random variable. So each of the random variables is just one of the standard, the normal random variable, okay? And then we repeat these sampling processes. That way, we obtain the multiple number of random variables, where each are corresponding to one Gaussian, or one normal random variable. But in this case of binomial random variable, the repetition is already included as the process of this binomial random variable, because binomial random variable is by definition is including or containing these repetitive sampling of 1,000 times, for example, or n times. Okay. So in this case, if we obtain one random variable from one binomial distribution, and then using that one value for our random variable, we can utilize that as that for estimating the probability p. How? We just simply divide a single random variable from binomial random variable by the total number of trials, which is our parameter for this binomial random variable. Okay? So that, again, in the previous cases, we considered multiple random variables, right? Xi, represented as an Xi. So X1 and X2 and X3 and so on. If we obtain 10 samples, and then each of these are one random variable, X1 through X10, and then computed their sample means. But in this case, we no longer see X1, 2, 3, and 4. We only see one random variable X, right? And that random variable is sampled from binomial random variable, and by definition, or the meaning itself of binomial random variable contains these repetitive sampling, right, from the Bernoulli random variable, right? So that way we see only one random variable, but in order to recover the probability p, we just divide it by n. In that way, the average value or expectation value of x over n will be the same as the true probability p. Okay, so x is following binomial random variable and p, and then we define the new random variable y as x over n. Okay, in this case, this random variable has the expectation value of p because e of x over n will be and p, right, divided by p n, and so it will be exactly as p. So in this case, let me ask one question. Is this new random variable y, is it biased or unbiased estimator for p? So as an estimator for p, is it a biased one or unbiased one? Is it biased or unbiased? Is it biased? If n is small. I suppose n, yeah, let's compare the two cases where n is 10 and n is 100. Then we consider two binomial random variables where the parameter n is 10 and unknown parameter p, and n is 100 and p. In this case, our random variable, let's call that as x1 and x2, and then in this case, x1 divided by n will be our new random variable y1, and that will be used as an estimator for p, right? And also in this case, so x2 divided by 100, and that is called x2, because in this case n is 100. So between these two different estimators, so they are two different estimators, and then in order to call, or in order to determine whether each of these random variable or estimator is biased or unbiased, we have to consider the sample mean. The expectation of this new random variable is, is it true or not in the first case? And also for the second estimator, y2, is this true or not? So both of them are true, right? So even though, so their expectation are both the same as the true parameter value p. So that way they are unbiased. And then, so we consider two different notions of biasness and also, what was the other one? What was the other property? Yeah, efficiency, right? So which one is more efficient? Yeah. So y2 is more efficient. And why? Why is y2 more efficient? Okay, then let me ask this question. What is the variance of y1? So again, y1, the definition of y1 is this guy. So what is the variance of y1? So this is an important part. So variance of y1 is 네? 네. 맞아요. So let me just derive this variance of y1. So y1 is x1 divided by 10, or in general x divided by n. And then let's see. So let me ask this simpler question. So what would be the number in this square? So in other words, when considering the new random variable 3x, what would be the variance of this 3x? In terms of the variance of the original random variable x. It's 9, right? It's 9. So in this case, we consider the new variable x divided by n. So in this case, the variance is n squared, 1 over n squared times variance of x, right? So variance of y1 or x divided by n is variance of x divided by n squared, and then the variance of an x is npq, which is just the variance of binomial random variable. So we we cancel one n in the numerator and the denominator. So the variance of our estimator is this PQ over n. And based on this variation, variance of this y1 and y2, since y2 has more, larger value for n, so the variance is smaller, and so y2 is more efficient, which means y2 is more focused. The distribution is more focused around the true parameter value p. See. Okay. So based on this mean value and the variance of our new estimator y, which is x over n, and then you guys know if n becomes larger and larger, and then p is not too small or not too big. So if if p is like a 0.9999 something, then in most of the cases you will observe the particular event is almost always happening. In that case, if n, even if n gets larger and larger, this distribution will not be similar to Gaussian distribution. But in the previous chapter, we learned that p is somewhere around like 0.5. It could be like 0.3 or 0.8 or so. So this p value is not really an extreme value, like a really big or really small. We exclude this part, these cases. So p is some value around 0.5. And then in that case, if n goes to large, n goes to really infinity, n goes to really large number, and then the binomial random variable, the probability distribution will be approaching, approximately the same as Gaussian distribution, right? So if n gets large, this x will be close to Gaussian distribution, and then our estimator x over n will also be Gaussian, because Gaussian divided by n will also be Gaussian, because n is just a fixed number. Okay, so x over n, which is our estimator for p, is Gaussian, following Gaussian distribution when n becomes large. And then what is the mean and the variance for our Gaussian random variable? So the mean value is p, and then the variance is pq divided by n, right? And so we can construct their interval estimate. So in this case, in order to estimate this p, true p, and then consider this confidence interval, which means the difference between the estimated value of p. So p hat here is defined as x over n, and then the difference of our estimator and the true value p. This will follow the Gaussian distribution, and then if we normalize this random variable by subtracting the true mean p divided by the true standard deviation, which is square root of pq over n, and then this one will follow the Gaussian distribution, standard normal random variable. And so we can also use this standard normal random variable z. Okay, so in this manner we can obtain this confidence interval. Okay, so in this case, in this equation, we see this p hat and q hat. So this hat means also we are using some estimator for p and q. So we were kind of happy because we were able to obtain the true variance value for our estimator x over n. But our variance will also have some unknown value. So we wanted to estimate the true p because we do not know that value. And then our estimator of x over n is following, the mean has the expectation of exactly the same, the true parameter p, but we have to know this variance part, right? But the p itself, which we wanted to estimate, is contained as part of the variance of our estimator, okay? So we wanted to estimate p, but that unknown p is also included in our variance of the estimator. So we have to replace this true p because we do not know this true value p. And so we instead use our estimator p hat. And then what is q? What is q? So q is originally 1 minus p, right? So if the true parameter was 0.61, and then the true parameter for q is just 1 minus p, which is a 0.39. Okay, so we have to use the true parameter p and q, but in practice we replace them with just our estimator p hat and also q hat, which is just 1 minus p hat. Okay, so this is how we obtain the interval estimate for some proportion. Yeah, proportion as an unknown parameter. Okay, let's see. And then similarly, we can compute this confidence interval, which is just this part. Okay, so that determines our confidence interval. And then also, if our boss is saying your confidence interval or your interval estimate has to be like within a particular range. So give me the estimate for the true parameter p. Okay, for example, we can consider the probability of some battery that explodes. Okay, so what is the probability of the battery exploding? Okay, suppose that probability was 0.2, and then your boss is asking you to give a interval estimate for this true parameter, and then you are only saying, okay, this parameter p is somewhere around 0.05 and then 0.35, and then your boss is not happy because it's too wide. Okay, so it could be either close to 0 or it could be as large as 0.3. So it is not acceptable interval estimate. So this is useless. So give me more tight interval estimate or narrower interval estimate. So if your boss is asking you such kind of a request, and then what you have to do is to just increase the number of samples, okay, in order to tighten or make this interval much smaller. So what is the required number of samples, or what is the parameter that is required in your binomial random variable? Okay, so this is our unknown parameter that we want to estimate, but you can still change this n, right? So given a particular range that your boss gave, so I want the estimate interval is like plus 0.1 and minus 0.1, and then depending on that, you have to choose the number of samples. Okay, then so let's look at this equation. And then this one tricky part in this equation is, in order to determine this n, you have to know this p and q values, right? So in the case of Gaussian random variable, we want to obtain, or we want to compute the interval estimate for the true parameter mu, or the true mean value, and then that value is not dependent on the true parameter mu. But in this case, in order to estimate the true parameter p, our required number of samples is also dependent on the parameter that we want to estimate. Okay? So in this case, we have to use this estimated version of p, but at the same time, apart from this equation, which is also dependent on the parameter p, we can make this equation independent of the true parameter p or estimated parameter p hat. So the idea is really simple. So p hat and q hat, that has some minimum or maximum value. And q hat, or in general, if we consider this p, and then it's just multiplied by 1 minus p. And we know p is between 0 and 1. And then if we just evaluate this equation, and then right? So this value is at least there. This is at most 1/4, right? 1/4. So we can change this guy as the maximum value, because that is the worst case, right? So that way we replace this value by 1/4, and then by just considering the worst case, the required number of samples will be changed into this form. Okay, so this equation is no longer dependent on the parameter p or p hat. Okay, and then we can extend this estimation of the proportion or some parameter for this Bernoulli random variable as this two sample cases. So now we consider two different populations, and then we have one binomial random variable n1 and p1, and then we have the second binomial random variable x2. Oops. Sorry for Okay, so that's it for today. I didn't know the class already finished it, and we will continue next time. Okay, thank you very much.
Well,